Spell checkers are something that we use every day and have come to rely on. But how are early spell checking algorithms able to determine when words are misspelled and then suggest a suitable replacement? As a human, we can see that this word should probably be learn, but how does a computer know how to do this? Even the 500 most common English words shown here would be a lot of possibilities that the algorithm would have to check. In reality, it's even worse, since the English language has about 171,000 words that are in common use, so our algorithm has to be pretty fast to keep up. Together, Robert Wagner and Michael Fisher set out to solve this problem and created the Wagner-Fischer algorithm in 1971 that can quickly compute the best replacement for a misspelled word. They improved upon the previous Levenshtein algorithm that was created 6 years prior in 1965 by Soviet mathematician Vladimir Levenshtein. Levenshtein's algorithm used recursion and was extremely slow, running in exponential time. This slowness is due to the 3 separate recursive calls for each pass through the algorithm. To fix this, the Wagner-Fischer algorithm uses dynamic programming to break the problem down into smaller subproblems that are much easier to solve. Their algorithm relies on the fact that to transform one word into another, say heat into another word, you must perform a series of simple operations. These operations could include insertions, which adds a letter, deletions, which removes a letter, and substitutions, which swap a letter for another. Using just a sequence of these 3 simple operations, it's possible to transform any word into another. Now let's look at how the Wagner-Fischer algorithm actually works. We'll use a table to find the minimum number of operations needed to transform the word bigger into bridge. We'll put each letter of bigger into the column on the left and each letter in bridge into the row on the top, starting with an empty character each time. Starting with the top left cell, how many operations does it take to transform an empty string into an empty string? Well, it takes 0 operations. How many operations does it take to transform an empty string into the string B? Well, it would take 1 insertion. How many operations does it take to transform an empty string into the string BR? It would take 2 insertions. We can then easily fill in the rest of this row and the first column using this rule. This step is what's known as the initialization step. Let's fill out the rest of the table now. We can look at the cells above, to the left, and diagonally up and to the left of the cell we're in. We can then take the minimum of those cells, which would be 0, and then if the last letter of the 2 words at this position are equal, we can just copy that minimum into this cell, so we can set this cell to 0. In the next cell, though, the tailing letters at this position are different, since B is not equal to R. In this case, we have to take the minimum and add 1, so we can set this cell to be 1. We can continue through the table following this rule until the table is completely filled out. The value in the bottom right corner is going to be the number of operations it will take to transform bigger into bridge. Although it's not explicitly used in this algorithm, we can even tell exactly what operations we'd need to take to transform bigger into bridge. We'll start in the lower right-hand cell and work our way back up to the top left corner. An insertion would mean moving left, a deletion means moving up, and a substitution means moving diagonally up and to the left. Each time we move, we always take the operation that will move us to the cell with the smallest value. Here we'll perform a deletion and move up. Then E is equal to E, so we'll perform no operation and move diagonally. G is equal to G, so we'll perform no operation, move diagonally again. Now we substitute G for D and move diagonally. Since I is equal to I, we again move diagonally and perform no operation. Then we'll insert an R at B and move left. And now we're on a cell that has a value of 0, so we can terminate our program. Let's look at the code for this algorithm. We can start by initializing the first row of our table to a list of sequential numbers. Then, looping through every row, we'll start by saving the previous row and setting the current row to the first sequential number, followed by zeros. Then, for each cell in that row, we can find the cost for performing an insertion, deletion, and substitution. Next, we add 1 to our substitute value if the tail letters are not matching. Then we set the current cell to the smallest operation. And finally, we return the total edit distance. This algorithm has a pretty impressive time complexity of O of A times B, where A and B are the length of each word. If we run this algorithm using a dictionary of n words, it becomes O of n times A times B, which you can see is much faster than the original runtime of the Levenshtein algorithm. Modern spell checking algorithms make use of artificial intelligence to suggest a word based on the context of the surrounding sentence. I hope that oh, I mean, I hope that you learned something. Thank you so much for watching.